Hi everybody, welcome back. This is now in sections of applications about exponential functions, and one of the most important are exponential growth and decay. So when you notice that you probably have seen this in a lot of math courses, and there's a good reason for that, because these equations come up in a topic known as differential equations, which you usually take after Calc 2. And they are kind of the first type of solutions that you get in this subject. So these things are an important deal in mathematics. So it's good to know how to work with them. So basically, exponential growth and decay in their simplest form will look like this. Well, the population is equal to some initial population, which we call P naught, times an exponential function times k, which is known as the relative growth constant, times some time t. If k is greater than 0, we'll have exponential growth, and if k is less than 0, we'll have exponential decay, which makes sense if you remember what we talked about in our intro to exponential functions video and the types of graphs you can have. Notice that all that P naught does is basically shift the graph up or down depending on the value of P naught, since P naught is a vertical shift or compression. So, first example we're going to have here is if the world population is about 6.5 billion people, and if the population grows continuously at a relative growth rate of 1.14%, what would the population be in 10 years? So we know that right now, so we're going to call t equals 0 right now. And we know that right now, the population is 6.5 billion people. And it's just easier to write 6.5 than 6,500,000,000 people, because just all those extra zeros just make things easier or harder to do, and you can always just divide everything by a billion to get rid of all the zeros, so it's easier just to write it like this. So, and then we want to know what it's going to be in 10 years. So we also have the rate, but rate always has to be in decimal form. So you divide by 100% and you get r equals 0.0114. And so our equation then is P equals 6.5 times e to the 0.0114, and then we want to know what it is at time t equals 10. So we times 10. And we just run this through our calculator. So I'm going to do that right now. 0.0114 times 10. And we get that we look like there's going to be approximately 7.284 billion people in 10 years. Alright, so that's the first example. So now here's a little bit more complicated example. Newton's law of cooling states that the rate at which an object cools is proportional to the difference in temperature between the object and the surrounding medium. So I wrote to the difference twice, sorry. That equation we don't know how to set up because that involves a little bit of calculus, so we can't set that up. But using differential equations, if you take that course, we can use whatever formula we get here to come up with an equation t that tells us what the temperature of the object is supposed to be for any time greater than or equal to 0. So we're just going to use this formula for now, and notice that it's just a transformation of an exponential growth or decay function, because this is really, in some sense, if I move the t naught to the other side, I really get t minus tm equals t naught minus tm e to the negative kt. So this is really my p, and this is really my p naught. So this is really an exponential growth or decay problem. So So the Tm is the temperature of the surrounding medium, and T naught is the temperature of the object at the time equals 0. So what we're going to do is look at the problem. Suppose that a bottle of wine is at a room temperature of 72 degrees, and it's going to be placed in a refrigerator to cool before a party. And if the refrigerator is at 40 degrees, and we note that the relative decay constant here is going to be 0.4, find the temperature after 3 hours. So we're going to use this formula T. The temperature of the medium. This is going to be the temperature in the refrigerator. So that's going to be 40 plus. And then the temperature of the object was initially at room temperature, so that'll be 72, minus another copy of the medium, times e to the negative 0.4, and we want to know after 3 hours. So all we have to do again is just run this through our calculator, so I'll do that really quick here for you. And we get but this is going to be approximately 49.64 degrees Fahrenheit. Alright, so that's all that's going to be to these problems right now. Once we get through 4 or 5, we'll be able to do more complicated examples with these types of problems, but right now this is just about evaluating them. So in our next video, we'll talk about the last application, the logistics equation. See you then.